So Andrew is actually going to talk about the extended Freycinet-Renner. We switched places, so you'll hear about that on Monday in the slot that says my name. So he'll still do that. I want to thank Lev and the other organizers for inviting us all to Parallel Lev. This has been a great conference so far. All right, so I'm going to talk about unambiguously local quantum physics and spacetime. This is basically the highlight. There's debate about whether Everett is actually a local theory. I'm going to argue that it's not local and that looking at reduced density matrices as a criterion is not a good way to establish locality. It's actually irrelevant to the question. But if I can show you a local hidden variable theory in space-time, which explains all of the entanglement correlations and Bell tests, and it uses localized separable packets of information that move on world lines, that will be an unambiguously local theory. Everyone will agree it's local. There won't be any room for debate. And I'm going to talk about a local many worlds theory that has that property. So the first thing you have to do is basically just forget what you know about Everett many worlds. I'm not going to be talking about global worlds at all. Those don't exist in this theory. Worlds are past light cones. So here we have 3 different observers. Each of them has their own past light cone, and each of those past light cone surfaces is the world defined for that observer. So there are no global worlds at all. And this is just special relativity. So this is just saying that we just take special relativity, the fact that we have perspectives that are limited by our past light cones, literally, then we're each in our own, world, at least until there are things in the intersection of our past light cones, down here for the purple and blue, and down here for the purple and orange. There are things in those intersections that we can agree on, and the speed of light is so fast relative to our experiences that we all tend to think the world is global, but we know that it's not. We know that when we look at the night sky, we're not seeing the stars now, we're seeing them millions of years ago. Or maybe at least 5 light years away or something like that. There is no present world that the observers agree upon according to special relativity. It's sort of a fictitious concept. But I'm going to take that even further. One more slide. So if you have 2 observers that happen to meet, their world lines intersect, they meet at a point, then the worlds that they're experiencing coincide. They have the same past light cone, all the same information. They could in principle share all the information they've collected, and so they can really agree about everything. So when you have observers meeting at an event, it's possible only then that they're in the same world. Now we're going to actually bring in the quantum theory part of this. One more step. Local ballistic model. So this is the local hidden variable theory that I promised you. We have local packets of information. They're all separable. These lambdas are not connected in any non-separable way to the other lambdas. They propagate on world lines, and there aren't any other missing particles in this diagram. Really, these should probably be straight lines, except at the intersections, because there's nothing else they're interacting with that would deflect them. But I don't think that's really a big problem. So the idea here is that we have lambda 1 and lambda 2 are information being carried by these particles. When they meet, they synthesize new information lambda 4, and then they both carry it off. The synthesis happens locally. The information that they both brought in is used locally to create this new information that they both carry out, and then lambda 4 and lambda 3 become lambda 5 here, lambda 4 and lambda 5 become lambda 6 here, and so on. So we're going to build the model up like this. This is the only stuff that's going to be in this model. It's going to be an unambiguous local hidden variable theory. And if you have this theory in spacetime, the causal structure is Lorentz invariant. The details of what's going on in the vertices will be Lorentz covariant, but the causal structure itself is Lorentz invariant. It doesn't matter what frame you're in. Okay. Now local many worlds. So we're going to replace the probability density in standard quantum mechanics with a fluid of point particles, and the density of that fluid is going to be given by the Born rule. So when a system is measured, the fluid subdivides its different outcomes. The proportions of those outcomes are given by the Born rule, and then experiences are tied to these individual fluid particles, and so after a big ensemble of runs, your experience of frequentist probability will be this weight. So you'll get the Born rule out of this fluid. There are some details about the mathematics you need to describe this fluid. It has to be infinitely subdividable, but that just means we need some new mathematical objects to capture this physics. There is a consistent way to do that. Okay, so a world for one of the particles in this fluid. So let me step back and be clear. So if I'm talking about one electron, it has a wave packet. I am talking about a fluid of point particles that make up that one electron. So it's actually, you can decompose the one quantum system into many, many copies, which basically each one acts like an electron, but they don't really interact with each other in the conventional way. They interact with each other to produce the wave dynamics that we see as this packet evolves. So there's really local interactions in this fluid that produce all of its wave properties, but it decomposes into point particles. Each one is in space-time, each one is on a world line, each one is carrying local information inside of it. Okay, so if you have a world for one particle defined as its past light cone, in addition to specific outcomes, this is where we go beyond special relativity and we actually need to talk about quantum theory now. So if I've done a measurement and there were two different outcomes that I could have gotten for the measurement, then I will have some of the fluid, say, let's just say half the fluid gets spin up for this measurement, half gets spin down. As soon as they have those different outcomes in their memory, that makes them different worlds. So if you have two particles that are at the same event, like here, but they've encoded different outcomes, they are still in different worlds. Even if they have the same past light cone, they haven't recorded the same information, the same sort of classical history about their past, about that past light cone. All right, so this is going to get a little bit technical. I'm not really going to have time to go into even a fraction of the details of this theory. So I'm going to try to get the highlights across. And then if we have time for questions, people can ask me and people can talk to me afterwards. And I have a paper on the archive. So yeah, so we're going to have all these fluid particles of a system S. So the system S is our electron. It has a bunch of different point particles in it. Each of those is carrying a local bit of information, which is like a wave function. And if you have a preferred basis at the macroscopic level, then each orthogonal term in those wave functions in that preferred basis corresponds to a different outcome, and that corresponds to a different subpart of the fluid, which is now in a different world. So the fluid of the electron has now split up into part that got spin up and part that got spin down. All of the fluids occupy one common spacetime. And only fluid particles that are in the same world, meaning that they have all the same past outcomes, interact in this fluid way. So that's where we'll see fluid wave effects. All right, so this is just to give an idea of how a measurement actually works in this theory. We're just treating the purple object as the ready state of a pointer system. And we have some microscopic system prepared in a superposition. For microscopic systems, the preferred basis is arbitrary. So I've just drawn this thing in this first part here to already be in the basis that the measurement is going to use. So now we measure this basis, and this is a local dynamical process. We have fluids from one system and fluids from the other. As they start to overlap, there are one-to-one interactions between those fluid particles. And when that happens, the memory in those fluid particles synchronizes like here. So we get this synchronization that happens, and that gradually divides the worlds up. So initially we have sort of the pre-interaction part of the fluid, and then down here you see the post-interaction part of the fluid. I've got multiple x-axes here, but it's all the same location in space. They're just separated so that you can see them, okay? But it's all happening in the same place in space-time. And so here, as this has happened, if you look at the two terms here, these are the two terms in this state. This corresponds to the transition from this state before the measurement to this state after the measurement. And the two orthogonal terms in this state correspond to two different fluids with different histories, different experiences. But there's a natural boundary as these overlap, because the particles are always getting paired off one-to-one. So we get a natural boundary for the evolution, and we even have dynamic boundary conditions for the evolution of the wave here, where the two blue ones are mapped or are linked at the boundary to the blue ones on the other side of the boundary. And then after the interaction is completed, they are well separated. So now I have just two fluids in space-time for one system, two fluids in space-time for the other system. And each one, what I've drawn here are the densities of those fluids, so the proportion of the fluid. And each one has this corresponding subscript, which is really a reference to what the outcome it saw for the other system was during the interaction. So I have the measuring device in state 0 having seen the spin as state 0, and the weight of that is A1. The density you see here is mod A1 squared. And I've just drawn this so the A and B are both half, but they could be anything. It doesn't actually matter. And then for the other half of the pointer, we have the other part of its fluid, so half of its fluid saw the state 1 because the particle was in the state 1. So the subscripts that get picked up here are records of the outcomes that you saw for the other system during a local interaction. Okay, now let's look at a Bell test and how we produce Bell correlations. So we're going to look at the Merman-Wigner Bell test. This is the one that has three spin setting measurements in the XZ plane, which are spaced by 120 degrees. So this axis, and this axis. And this is a kind of a classic example of Bell's theorem. It's nice because by symmetry, we only actually need to consider two different measurement settings. There's the case where Alice and Bob measure aligned directions. So that's what I've got here. Here is the singlet state that's been prepared at some source. So you see, if you look at these terms for the blue one, we've got the singlet state. This is the particle 2, this is particle 1. These are just different, each one of these contains the whole state, this state right here. And then these interact with Alice in her ready state and Bob in his ready state. And the way this is drawn, this measurement is sort of fictitious. It's like a local spin-spin interaction where there's just no coupling to the dynamics of the wave packets themselves. So the only degree of freedom that's getting coupled here is the spin of these particles as they cross. I don't think there's a real Hamiltonian that works like this, but it simplifies the discussion and you get the right intuition from it. So what happens is that over on this side, Bob interacts with qubit 1. And so Bob evolves into this state here. And this is now the local information that's going to be carried away by all the copies of Bob and by all the copies of particle 2. So that's our local ballistic synthesis of the information. And over here, and also I should point out that Alice is not even in this state. She hasn't interacted with Bob yet at all. So we had this, we had system 1 and 2, they interacted. Then 2 goes off to Bob, and he interacts with it. And he picks up a record of system 1 as well, even though he hasn't interacted with it, because system 2 was already carrying that record. Okay, the same thing happens for Alice. Alice measures particle 1. She picks up a record of particle 2, but she has this local state. It doesn't have Bob in it. Bob's not entangled with that state. Okay. And now finally, they meet up later on. So it's actually important to point out here that at this point, I've just got, in space-time, I've got Alice's who got 1, Alice's who got 0, Bob's who got 1, Bob's who got 0. There is no correlation yet. These are the statistics of the maximally of the reduced density matrices on both sides. So they're just not correlated at all. But now, Alice and Bob exchange signals. I've just drawn that as they meet. So they're moving at the speed of light here. So they exchange signals, and as soon as that's happened, as soon as information has gone from one to the other at the speed of light, now they get paired up, because now when they synchronize, they pick up the unitary evolutions from this interaction and from this interaction. And so now I have an entangled state of all 4 of them. And that entangled state tells me automatically which Alice's meet which Bob's. It says, okay, the Alice's who got 0 meet the Bob's who got 1. And the Alice's who got 1 meet the Bob's who got 0. And so in the experience of all the Alice's and all the Bob's, the entanglement correlation has been obeyed for this state. But it was not obeyed until this event where they got together in the future locally. That's when the entanglement correlation becomes physical in this theory. There simply was no correlation when they were still space-like separated. Okay. Here's the other setting we need to consider. Alice's measurement looks the same, but Bob's is now in a different basis, which is, so Alice and Bob don't measure parallel settings. By symmetry, this is all you need to consider to reproduce the entire experiment. So we can go through the same analysis. Over here, if you look, I've got Bob's with different histories for particle 1, but the total weight of them is still half for 0 and half for 1, so I still have the stats of the reduced density matrix, still maximally mixed on both sides. There's still no correlation while they're here. And then Alice and Bob meet, they become correlated, they get paired off in these proportions, and now again, the entanglement correlations for that state have been explicitly obeyed, and it was all done locally in space-time. Everything was on world lines. So we get all of the correct entanglement correlations for the Bell test, and indeed this mechanism produces any and all entanglement correlations. And even more generally, take your favorite quantum experiment. This model gives you the local hidden variable explanation of that experiment. It's all pretty trivial to get out of the theory. Okay, so now I'm going to attack some claims. So there's this claim that Everett-based theories are locally causal because if you measure just one particle in an entangled state, the statistics of the other particle don't change, instantaneously. And that's certainly true, but I don't think that really has anything to do with the underlying question. If you've got a non-separable state, then there is only one non-separable state. The reduced density matrices are not separate things. They're just aspects of that one object, akin to shadows or projections on a particular axis. But you're really talking about just one object. you can't separate it into parts and try to talk about the parts separately, or you've like undone the non-separability through verbal semantics. But it's really not the right way to think about it. Really, when you've changed psi, when a measurement on particle A changes psi to psi prime, the reduced density matrix has changed for Bob from trace over A psi to trace over A psi prime. The object that is there, the only object that's there in the theory, is different now. It has changed. So whether or not you want to call that action at a distance or local causality, that's a little bit subjective. Kind of depends on how you define causality. But in the theory, the underlying structure has changed. And I think Lev has been making this point that the wave function is non-separable. It changes whether or not you want to call that action at a distance. I don't think that's a good criterion for locality. I think this is a non-local change in an object that's in the theory. So really, the argument is basically claiming that if I've got two objects that cast the same shadow, those must be the same object. I think we all agree that's nonsense. And I think that's pretty similar to what's going on when you talk about the reduced density matrices by themselves. Okay, the last little detail here is that there in space-time state realism, and I think from talks from Lev and some other Everett people, there's this idea that, Alyssa mentioned it too, that when Alice does a measurement, there's a wave front of branching that happens that goes out from Alice, and when it reaches Bob, or when the signals from Alice and Bob reach some common observer, only then do they actually join a world. And that's totally consistent with what I said here. Once they actually get together, they're going to meet, and they're going to, now at this point, become correlated, end up in worlds together, just like in the Bell test cases. The problem is that the formalism in these theories has these non-separable objects, and those wave fronts are just nowhere to be found in those theories. They're not part of the mathematical structure of the theories at all. They're like a semantic addition that you make. It's a verbal claim. And the virtue of these local hidden variable theories, the local many worlds theory, is that those wave fronts are explicit. They're built right into the theory. They're in the math. They're unambiguously there. Okay, non-separable theories are also not Lorentz covariant. And this is a claim that I hear, and again, this is, I think, just kind of verbal semantics. The claim is sort of that quantum field theory is Lorentz covariant, and so whatever we're saying about interpretations of quantum mechanics should be Lorentz covariant. But I think this is sort of like mixing apples and oranges. If you look at what a Lorentz transform actually is, it's a mapping between the description of an event in one frame. It just takes information inputs about that one event, and it produces the description of that same event as seen in another frame. But if you look at a non-separable theory, like space-time state realism, you've got a state that's at a point in space, but that state refers to information about other events in space-time. Some of them are space-like separated. And when you map from S to S prime in that theory, you need to use inputs from those other points. And so that mapping you're doing, whatever it is, it's not a Lorentz transform. And so to claim these theories are Lorentz covariant is, I think, just a logical mismatch. Whatever you're talking about here, it's not a Lorentz transformation. You don't have four vectors, you don't have field tensors. You just don't have those objects in the theory. Or at least they're not the fundamental objects. So this actually is not a new point. Relativistic quantum field theory was developed using a separable Lagrangian formalism and the Heisenberg picture. You're going to hear on Monday a number of talks from people who work on the local Heisenberg picture. But if you want to kind of work in the framework that I've been working in, where we talk about wave functions and packets in space-time, you have to kind of go to a local Schrodinger picture. And Schwinger identified this discrepancy in 1948 in this paper I've cited here. He pointed out that the Schrodinger picture and Heisenberg picture are equivalent. It's just a matter of like how you interpret which objects the unitaries act on. But once you go to the local Heisenberg picture built on this local Lagrangian formalism, it's not equivalent to the standard Schrodinger picture anymore. It's actually a separable theory. And he derived the evolution, he came up with state vectors that live on space-like hypersurfaces and then showed how they evolve in a covariant way. And so they respect things like information from the past light cone stays, or you can't have information here that comes from outside the past light cone of an event. So I think the takeaway here is that you really can't mix the intuition you get from the non-separable kind of theory before you put the relativity in and the separable theory you get after you put the relativity in. Or if you do mix them, you have to be extremely careful how you do it. So the local many worlds model that I've been talking about, it has all of this Lorentz covariant structure. It's consistent with the model that Schwinger came up with. It's not the same exact model, but it's consistent with it. Okay, why would we want non-separability anyway? So let's suppose we already want a local theory, and we already want to use the Everett explanation of measurements. So there is no collapse, just a branching into multiple outcomes, and you have weights for those outcomes, different ideas about how you would get those weights. But given that you want those two things, why would you choose the non-separable, non-Lorentz covariant theory that doesn't have the wavefronts in it over the separable one that does have the wavefronts in it? Why would you make that choice? So that's really the question here. Why would you want to stick with that theory when it comes with all of these conceptual costs? You have to give up Lorentz covariance. You have to give up separability. So all of this very natural intuition goes away when you do that. So this slide, I'm going to try to illustrate all of these points. So here is the local many worlds theory. So we have a source. It produces this state, so common information that goes out to both qubits. Alice does a measurement. I've drawn this in a frame where their measurements are not simultaneous, but they are space-like separated. Oops, sorry. So Alice measures. So now we have the state of all three of those objects, particle 1, particle 2, and Alice, just like I showed in the Bell slides. Bob measures, and now over here, there's a state of particle 1, particle 2, and Bob. Again, it's just local synthesis of the information. And then finally, when we get to here, we have a state of all four systems, and now the outcomes are correlated according to the Bell correlations, the way we expect. But let's compare that to the non-separable theories. So the non-separable theories say, when I prepare the state at the source, I have a non-separable object, psi1, 2. Yeah, it's true that I can only access it by doing measurements at the locations of the qubits, but it's a non-separable object. It's a single object, and so I've drawn it as one object here to really emphasize that point. And now, when Alice does her measurement, that object evolves. So even over here for qubit 2, this state has changed to be psi1, 2a. I am arguing that when that happens, that is a change in qubit 2, because qubit 2 is not an independent object. It doesn't have, its reduced density matrix is not an independent object. It's just a property of this state, okay? And now when Bob measures, now we have this state, and so the correlation is established even when Alice and Bob are still space-like separated. And this is what leads to all of the typical Bell violations. Another thing we can see in this slide is that, this slide allows us to illustrate the narratability failure that Albert talked about. If I boost to another frame where Alice measures after Bob, this state here simply never exists in the narrative. Instead, this state here exists, and then it's this one. So the two narratives are different. We have a different evolution in the two different frames. And I think that's another fundamental problem with these. There should be one consistent narrative, and it should be Lorentz covariant if we want a local theory. And then finally, why would you want non-separability? So if the goal is to say that, like in space-time state realism, and I think Lev will say the same thing, it's only here at this event where Alice and Bob actually become correlated. Only when they meet up together, now Alice and Bob are in a world together. But they already had this non-separable state before that, and having that non-separable state created all of these problems. It makes the theory not Lorentz covariant. And if all you needed was to have the correlations here at the end, why would you not just use this theory? This theory has them there. At the first time that you're trying to say there's a correlation between Alice and Bob, this theory does that. So why do you insist that there's this non-separable object that's there beforehand if it doesn't do anything for you in your theory? What's the point of having it if you only need this object to be there when the two systems get together at an event? Why have a non-separable object instead of just copies of local memory? Okay. All right, so basically a repeat of my intro slide. So whether or not I've convinced you that non-separable theories are local and they're not Lorentz covariant, there's clearly some ambiguity. There's enough room for us to debate the point. And if you take this local many worlds model, which again I did not go through all the details of, I glossed over a lot of details, you will end up with a Lorentz covariant theory, and it's fully consistent with relativistic field theory. There are some details I didn't mention. So you can do all your favorite pet experiments. You can find the local hidden variable theory for those experiments. The same mechanism actually produces interference effects, and it also explains like local collapse, Einstein's original concern. Like I just send a particle through a beam splitter, and it goes to one of two detectors. But now, in half of the fluid of this detector fires, half of it fires over here, and when they come together, the one that fired over here gets matched to the one that didn't over here, and vice versa. And so now we have a local explanation for wave function collapse for a spatially extended wave function. So this model, it kind of resolves everything. There are details to work out, but it's in space-time. It has local hidden variable theories. It's Lorentz covariant. It's local in a way that I don't think anyone can argue with. So you just have to go through all the details and see how all the little parts of it work to convince yourself that you have a viable theory here. All right, thank you for listening, and thanks again to the organizers. Sorry, give me 1 second.
Thanks. So I want to take the opportunity to say something that's come up in a few of the talks. I think there's something strange about describing sort of a standard Everettian line as if saying that the quantum state is an object. It's a state. I mean, I've got a, it's a representationally complete description of whatever the physics is. It's quite neutral as to how.
But it's non-separable, right? I mean, that's the part.
Sure, but well, if I can finish. So look, here would be a really silly argument, and this is not your argument, but here would be a really silly argument that classical electromagnetism is non-separable. You could say, well, I can do classical electromagnetism on a Hamiltonian formalism. There's a single point in the state space which describes things, and that point changes as soon as I do something anywhere. Therefore, the theory is non-local.
Yeah, I would say that if you make that your fundamental physics, that would be non-local. Yes.
Okay, right. But what does it mean to make that the non-local physics? I mean, the point is the state description there is a state.
Yeah.
It's a summary of lots and lots of local information. So in the quantum state, in the quantum theory, likewise, it's a state. It's representationally clear. If you ask, what is it representing? It's representing physical features of lots and lots and lots and lots of systems. So just in the electromagnetic case, if you want to know is the theory non-local, you want to know, do the features of the state that represent system B change when you do something to system A?
Yeah.
If you ask exactly the same question in the quantum case, you'll get exactly the same answer. If I've got particle B that's over here in a localized region, and I've got particle A and particle C that are interacting, then even if particle A and particle B are entangled, the partial trace of over the rest of it of particle B will not change if A and B change.
Yeah, I mean, I said the same thing, yeah.
Well, actually, on your slide, you kind of don't. You say that the partial traces are different. I didn't understand that at all.
I say that the statistics are the same. I mean,
go back to
that's the point. Oh, sorry.
If we go to the previous slide.
Yeah,
so your bullet point 3, I really don't understand. It says it instantaneously changes the reduced density matrix of
Well,
B.
it certainly changes the definition, and so if
right, but trace A psi psi equals trace A psi prime psi prime.
Yeah, I understand that once you do this and look at the statistics, you have the same local measurement statistics, but the actual object that you've got in the theory is this one non-separable relation, whatever it is, and that relation is extended and it changed.
Right,
So again, yes, the statistics did not change, but if you have a commitment that this non-separable object is a fundamental part of your theory, that thing changed.
But I don't understand what it would mean to say it's a fundamental part of your theory. It's the state of the system. It's not a fundamental part of your theory any more than the Hamiltonian state
Well,
is.
no, it is. You need that relation to produce all of the correct empirical facts. When Alice and Bob meet, if you don't use the full state, you won't be able to match
Sure,
them
but
up
that wasn't
correctly.
the claim. The claim is an unlocality case. I mean, look again at your bullet point.
Well, again, this is, I mean, I know that we don't all agree about this. My point is that if you want to define local causality as saying the reduced density matrix didn't change, then I agree. That's a fine definition. But if you want to say that nothing in my theory changed, I would say that's wrong.
Well, again, something in my theory changes if I do classical electromagnetism. The state of the universe
Well, again, that was why I went
the
back to
state
this
of the
slide.
universe depends on what happens anywhere.
If you look at classical electromagnetism, it doesn't follow this structure at all. The thing you're talking about is not one of these lambdas. It's
I
a
could write down the
delocalized
state of the
description.
universe in your theory here if I like. I mean, it's a free country.
Sure, but what I'm talking about is a theory where all of the information that is produced happens in this local ballistic way.
I'm not asking about your theory here, and I think your theory is really interesting and worth exploring. I'm just saying I think what you're saying about the other version of Everett is just false.
Yeah, again, I think it's not false, it's just subjective. It depends what you mean. Yeah.
I won't iterate that, I don't take too much time.
Thank you. It was a really great talk. Could you maybe quickly elaborate what the function of the hidden variables is in particular? Why do you need them, or why do you need hidden variables additionally to the states?
Oh, the states are the hidden variables. I was just,
okay.
I was kind of talking about that before I even started talking about quantum theory. It's like if you have this, it doesn't matter what's quantum theory or any other theory, everyone will agree this is local.
Okay.
No matter what those lambdas are.
Okay, thanks.
Yeah.